Welcome to today's class. In today's class, we will discuss some problems on character tables. These problems are taken from previous NET exams. If you remember, in last two classes, we have discussed how to identify IR active and Raman active vibrational modes. So let's solve these problems to get bit more detailed understanding. So the question is, IR active normal modes of methane belong to which irreducible representation? So as we know, methane belongs to tetrahedral point group and the character table is given. Now we want to identify IR active normal modes. As I have discussed in the previous two classes, our main interest is the symmetry of the function psi e mu psi g. So we need to investigate what is the symmetry of this function. Psi g is the vibrational ground state, mu is the dipole moment operator, and psi e is the vibrational excited state. So vibrational ground state is always represented by A1. Psi g is always A1 because vibrational ground state corresponds to vibrations at absolute zero, which are always symmetric. So psi g is A1. Then we come to psi e mu. If the total function should be A1, then psi e mu should also be A1. As we know, any function, any irreducible representation AI multiplied by itself will give A1. So if one is A1, of course the other should also be A1. So we are left with psi e mu. Psi e is the excited state wave function and mu is the dipole moment operator. Both should belong to same irreducible representation. That means if psi e belongs to some ai, mu should also belong to the same ai. Then only we will get a1. Otherwise we will not be able to get a1. So first we will check to which irreducible representation mu belongs to. Mu is the dipole moment operator. As you know, it has components mu x, mu y and mu z. So x, y and z components belong to T3 irreducible representation. Therefore, automatically psi e also should belong to T3 irreducible representation. Because if you multiply T3 by T3, you will get 3 3s are 9, 0, minus 1 into minus 1, 1, minus 1 into minus 1, 1, minus 1 into minus 1, 1. So you basically get 9 times A1. As I told you, either it should be A1 or it contains A1. So T3 into T3 is A1. Therefore, this transition is allowed. So the right option is T3 because dipole moment belongs to T3. The excited state or the active normal mode should also belong to T3. Okay, so now we'll proceed to the next problem. Now let's start with the second problem. The transition that is allowed by expolarized light in trans-butadiene is. So the C2H character table is given. Trans-butadiene belongs to C2H point group. So they have given expolarized light. So that means we have to take the X component of the dipole moment and this belongs to Bu. So I have written mu X belongs to Bu irreducible representation. As we have repeatedly said, we are interested in symmetry of psi e mu psi g, but here expolarized light is given, so we have to consider psi e mu x psi g. Mu x we already know the symmetry, and what symmetry psi g and psi e belongs to, these we will find out based on the four options given here. The first option is AU to AU. So let us try this. Let ground state be AU and excited state is also AU, but the dipole moment is BU. Mu x is BU. So let's multiply these three. This is called triple product AU, BU into AU. So if I do this, if you just multiply this, so I will get simply BU. So this is not equal to A1G. So this A transition is forbidden. Second option I'll consider. Second option, ground state is AU, excited state is BG. And dipole moment, of course, it is BU. So I multiply this 3. AU into BG, if you just multiply the characters from this table, AU into BG gives 1 into 1, 1, minus 1 into 1, minus 1, 1 into minus 1, minus 1, minus 1 into minus 1, 1. So you get this. Then you multiply this with BU. So you get 1 into 1, 1, minus 1 into minus 1, 1, minus 1 into minus 1, 1, 1 into 1, 1. So finally you get AG, the most symmetric representation. You should get either A1, A1 or A1G. A1G or AG are both same. So A1G is nothing but AG. So we got A1G for this transition. So the option B is allowed transition. So the answer is option B. Anyway, we'll check option C and D and see whether they are allowed or forbidden. So here ground state belongs to BU, excited state belongs to BG. So you can multiply BU and BG, the second row and fourth row in the character table. If you multiply, you get 1 into 1, 1, minus 1 into minus 1, 1, 1 into minus 1, minus 1, minus 1 into 1, minus 1. And then again you have to multiply this by BU. After this you will get 1 minus 1, 1 minus 1. So you will get basically BU, you don't get AG. So this is also a forbidden transition. Similarly, you can also check for option D. It is also a forbidden transition. So the simple thing here is you have to multiply the characters of the 3 different symmetry functions. You take the triple product. Here G is ground state, that is the first, the one lying to the left of the arrow, and the excited state is the one lying to the right of the arrow. X polarized light means you have to take mu x, which has BU. So once you evaluate this triple product, you will see whether you will get AG or some other representation. If you get AG, then the transition is allowed. If you don't get AG, then the transition is forbidden. Let's proceed to next problem. So let's read the problem first. For H2O molecule, the electronic transition from ground state to excited state of B1 symmetry is. So for H2O molecule, we know that it has C2V point group. Here, last 2 questions we are interested in vibrational transitions, that is IR active vibrational modes, but this question is different because here we are talking not about vibrational transitions but electronic transitions. So we have to be careful. So as always, we are interested in the symmetry of psi E mu psi G. Here excited state symmetry is given in the question as B1. So we know that excited state has B1 symmetry. Ground state, ground electronic state, if a molecule is a closed shell molecule, then ground electronic state always has A1 symmetry. The reason is that each orbital contains, basically in a closed shell molecule, any orbital has 2 electrons. So if we have some arbitrary symmetry for one electron, let's say Ai, and we multiply with the same Ai, we get A1. So for each orbital we get A1, and you multiply the symmetry of all the orbitals, the final symmetry will also be A1. In general, for any closed shell molecule, the symmetry is always, ground state electronic state symmetry is always A1. However, for open shell molecules, this is not the case. In case of such molecule, you have to consider the symmetry of orbital that contains the unpaired electrons. So this is how we determine the symmetry of electronic states. If it is closed shell molecule and ground state, then it is A1. If it is an open shell molecule, then the symmetry of the wave function is the symmetry of the orbital with unpaired electrons. So here water is a closed shell molecule, so the ground state symmetry is A1. Therefore, psi E mu should also be A1. So since ground state is A1, psi E mu should also be A1. Here psi E is already given. Psi E has, excited state has B1 symmetry. Since excited state has B1 symmetry, dipole moment should also have the same symmetry. Otherwise, the product is not A1. So psi E is B1. Therefore, dipole moment should also have B1. Then only we will get A1. Otherwise, we will get something else. If you see this B1 representation, here X component of the dipole moment is there. So the transition is allowed with respect to X polarization. So the option is B. The transition is allowed with X polarization. It is not allowed with Y polarization or Z polarization. Because if you consider Y polarization, then it will become B1 into B2, which is not equal to A1. If you consider Z polarization, then you will get B1 into A1, of course, which is not is equal to A1. So let's proceed to the next problem. The irreducible representation of C2H are AG, BG, AU and BU. The Raman active modes of trans 1,3-butadiene belong to irreducible representation. Okay, so here trans 1,3-butadiene belongs to C2H. In C2H, there are 4 irreducible representations: AG, BG, AU and BU. Here we are asked to identify Raman active modes. So keep it in mind. So in first 2 problems, we talked about IR active vibrational modes. In third problem, we talked about electronic transitions. Here we are talking about Raman active modes. For Raman active modes, instead of psi E mu psi G, we are interested in psi E alpha psi G symmetry. Here alpha is the polarizability. As we have already discussed, vibrational ground state is always A1. Therefore, psi E alpha should also be A1. Or in this case, since here AG is there, instead of A1, we simply write as AG. So psi E alpha should be AG. G is Garrett or even symmetry. Alpha is a polarizability tensor. It has components x square, y square, z square, xz, yz, zx. All these components x square, y square, z square, xz, yz and zx are all even functions. Even functions are represented with Garrett or G symbol. So since alpha belongs to Garrett, psi excited state should also belongs to Garrett. Then only we'll get a Garrett representation or A1 representation. So in the answer, there should be only Garrett functions but not ungarrett functions. The option is AG and BG, or AG or BG. We can say either both should belong to AG or both should belong to BG, because all these functions are Garrett functions. That's why polarizability has Garrett symmetry. Therefore, excited state should also have Garrett symmetry. Then only we'll get a overall Garrett symmetry. So the option here is A. Let's go to problem 5. The character table of irreducible representation A1 in C3V is given below. Identify the representation that is orthogonal to A1. So here we are not talking about any IR activity or Raman activity or allowed electronic transitions. Here we are talking about orthogonality theorem. Basically, the question is we need to identify among these 4 representations which is orthogonal to A1. So orthogonality, as we have discussed, is take the dot product of the 2 vectors. If the dot product is 0, then A and B are orthogonal. If it is non-zero, they are not orthogonal. Here, while taking dot product, one important thing we need to remember is we have to consider the weights of these symmetry operations. E has weight of 1, C3 has weight of 2, sigma V has weight of 3. So when we take the dot product between A1 and these vectors, we have to multiply by 1, 2 and 3. So let's do it. So the options here are tau 1, tau 2, tau 3 and tau 4. Let us take tau 1. Tau 1 is 1 minus 1, 1. So 1 multiplied by 1, 1 multiplied by minus 1, 1 multiplied by 1. We have to multiply this by 1, 2 and 3. So 1 into 1 into 1. 2 into 1 into minus 1. 3 into 1 into 3 into 1 into 1. This term. So finally we got 2. Similarly, we take a1 into gamma 2. So we got 0. a1 gamma 3 we got minus 1. a1 gamma 4 we got minus 4. So for option B or gamma 2 we got dot product 0. So a1 and gamma 2 are orthogonal to each other. So the most important thing is we should not forget to multiply by the weights. Okay, so this is how we solve problems related to orthogonality theorem. So thank you. Probably in the next class we will discuss some more problems on character tables.